In this video we're going to be looking at probability density functions, and again we're trying to find k. However, this time instead of using integration we're going to be using the formula of normal 2D shapes based on what we see from when we plot the graph. So let's have a look at how this could work in this question. Now, just to note, this is normally only ever going to work when we have linear graphs, because that is what creates a polygon of some shape. If we have quadratic or cubic graphs, we're going to have curves which are not going to work for us. So the first step is always to sketch the graph, and part A asks us to sketch the graph of fx. So let's start by doing that. So here's my x-axis, here's my fx axis, and we know that x is between 0 and 1 for when x is a half, and 1 to k. So x is between 0 to 1 for the first part of the graph, and for the second part it's between 1 and k. We're not sure how far along that is, it's just a random distance. So the graph here of a half is just a flat line at the height of a half. Now the second bit is where x minus a half. We're told that k is a positive constant. So I'm going to assume, although it doesn't actually really matter, that k is bigger than a half, so that a graph will be starting at 1 and going up to there at a height of k minus a half. So now we have two distinct shapes in our graph. So part A is done, we've sketched the graph. Now we need to show that k equals a half times 1 plus root 5. Well, we know that the entire area under the graph is 1. So we also know the area of shape A, which is this rectangle. The height there is a half, and the length of it is 1. So the area is 0.5. So that must mean that the area of our trapezium here, made by the second part of the function, or by the second function, is also 0.5. And what we have there is a trapezium. So if I draw that out here, we know that this height here is 0.5. We know that this length in between the two parallel sides is k, and we know that the height is k minus a half. Sorry, this height here, this one, is not k. In fact, it's k minus 1. So that height there is k minus 1. And we can use this information in the area of a trapezium formula to find what k is. So that is the area of a trapezium, and we know that the area of our trapezium here equals a half. So let's substitute in our values. A plus b are the two parallel sides, so we've got 0.5 plus k minus 0.5, or a half, divided by 2 times the height, which is k minus 1, and that equals 0.5. I'm going to multiply through by 2, so I will get 0.5 plus k minus 0.5 times by k minus 1 equals 2 times 0.5 is 1. Can cancel these two terms, and expand the bracket, so we'll get k squared minus k equals 1. So now to solve k, we need to equate our quadratic to 0, so k squared minus k minus 1 equals 0. So now we need to complete the square on this. So we will have k minus a half all squared minus 5/4 equals 0. If we rearrange this to solve for k, k minus a half squared equals 5/4. Therefore k minus a half equals the square root plus or minus the square root of 5/4, which is plus or minus root 5 over 2. And then k equals half plus or minus root 5 over 2. Now we're supposed to show that k equals half times 1 plus root 5. So we need to show that k equals half times 1 plus root 5. So what we can do here is factorize these two terms to get a half outside of 1 plus or minus root 5. And we know that it's not negative because 1 minus root 5 will give us a negative answer, and if k was negative it would mean that our PDF would go below 0, which would not make it a valid PDF. So k must equal a half of 1 plus root 5. So in this video we've looked at how we can use the area of regular shapes such as rectangles and trapeziums, and how they can help us to find the variables when we have a graph which does not have any curves and is just built by straight lines. We can almost always find a compound area from graphs such as these.